On April 26, 1986, at precisely 1:23 a.m., a catastrophic explosion tore through reactor number 4 at the Chernobyl nuclear power plant in Soviet Ukraine. The explosion was so powerful that it blew the 1,000-ton steel and concrete lid off the reactor core, sending it spinning into the air like a coin. But this was no ordinary industrial accident. What happened in those early morning hours would set in motion a series of events whose consequences we are only beginning to fully understand nearly 4 decades later. The immediate aftermath was horrifying. Flames shot hundreds of feet into the night sky as graphite reactor components burned with an intensity that reached temperatures of over 2,000 degrees Celsius. Firefighters arrived within minutes, completely unaware that they were being exposed to lethal doses of radiation. Many of these brave first responders will be dead within weeks, their bodies literally consumed by radiation sickness. But what makes Chernobyl uniquely terrifying is not just what happened that night, but what continues to happen today and what will continue for generations to come. The explosion released approximately 400 times more radioactive material than the atomic bomb dropped on Hiroshima. Radioactive isotopes of iodine, cesium, strontium, and plutonium were blasted into the atmosphere and carried by wind currents across Europe, contaminating an area of over 150,000 square kilometers. Within days, radiation detectors in Sweden, over 1,000 kilometers away, began registering abnormal levels of radioactivity. The Soviet government initially tried to cover up the disaster, evacuating the nearby city of Pripyat only 36 hours after the explosion, by which time residents had already received dangerous doses of radiation. Today, when we think of Chernobyl, we often focus on the immediate death toll of 31 people in explosion and acute radiation sickness cases, or the estimated 4,093,000 additional cancer deaths predicted by various studies. But there's a far more insidious, hidden danger that lurks in the contaminated zone, one that scientists are only now beginning to fully understand, and one that poses unprecedented risks for centuries to come. The true hidden danger of Chernobyl is not just the radiation that was released in 1986, but the ongoing radioactive threat that continues to evolve and spread in ways we never anticipated. Unlike a bomb that detonates and disperses its radioactive payload in a single moment, Chernobyl created a permanent radioactive source that continues to contaminate the environment through multiple pathways. The damaged reactor core still contains approximately 200 tons of nuclear fuel and radioactive materials. This material is slowly degrading, creating radioactive dust that can be dispersed by wind, water, and increasingly by forest fires that rage through contaminated red forests surrounding the reactor. Recent studies have discovered that radiation levels in certain areas of the exclusion zone have actually increased in recent years, not decreased as scientists originally predicted. The radioactive contamination has seeped deep into the soil, entered groundwater systems, been absorbed by plants and trees, and accumulated in the bodies of animals that roam the zone. These organisms are now mobile radioactive sources, capable of carrying contamination far beyond the boundaries of the 2,600 square kilometer exclusion zone. What makes the situation particularly alarming is that we are dealing with radioactive isotopes that have half-lives ranging from days to tens of thousands of years. Cesium-137, one of the most abundant contaminants at Chernobyl, has a half-life of 30 years, meaning it will take over 300 years before it decays to safe levels. Strontium-90, which accumulates in bones and causes bone cancer and leukemia, also has a 30-year half-life. But even more frightening is plutonium-239, which has a half-life of 24,000 years. This means that the plutonium released from Chernobyl will remain dangerously radioactive for thousands of generations into the future. The question is not if this radioactive material will continue to spread and pose risks to future generations, but how and to what extent. Scientists have identified several critical pathways through which Chernobyl's radioactive legacy will continue to threaten human health and the environment for centuries to come. These include the structural instability of the containment structures, the spread of contamination through wildfires, the migration of radioactive particles through groundwater, the concentration of radioactivity in biological organisms, and perhaps most concerning, the potential for genetic damage that could be passed down through multiple generations of affected populations. In the months following the disaster, Soviet authorities faced an unprecedented challenge: how to contain a burning, highly radioactive reactor core that was still emitting lethal levels of radiation. The solution they devised was both ingenious and terrifying in its inadequacy. Between May and November 1986, approximately 400,000 workers, many of them Soviet military personnel and civilian volunteers who would later be known as liquidators, constructed a massive concrete and steel structure over Reactor 4. This structure, officially called a shelter but commonly known as a sarcophagus, was built under extreme conditions with workers limited to exposure times of just minutes before reaching their maximum allowable radiation dose. The structure was essentially a massive concrete shell supported by steel beams, designed to contain the radioactive debris and prevent further release of contamination into the environment. The sarcophagus was always intended as a temporary solution, designed to last perhaps 20 to 30 years. Engineers knew from the beginning that it had significant structural flaws. It was constructed hastily without proper foundations, using radioactive materials from the destroyed reactor building itself. Parts of the structure were assembled remotely using cranes and helicopters due to the extreme radiation levels. As a result, the sarcophagus had numerous gaps and cracks, some large enough for birds to fly through, allowing rain, snow, and air to enter and potentially carry radioactive particles out. By the mid-1990s, just a decade after construction, the structure was showing serious signs of deterioration. The steel supports were corroding, concrete was cracking, and there was genuine concern that the entire structure could collapse, potentially releasing a massive cloud of radioactive dust that would contaminate a vast area. The international community recognized that the aging sarcophagus posed an unacceptable risk, leading to the development of the New Safe Confinement, or NSC. This extraordinary engineering project, completed in 2016 at a cost of over 1.5 billion euros, is one of the largest movable structures ever built by humans. The NSC is a massive steel arch structure measuring 257 meters wide, 162 meters long, and 108 meters high, tall enough to completely cover the sarcophagus and the remains of Reactor 4. Weighing approximately 36,000 tons, the structure was assembled next to the reactor and then slid into place on rails, a necessary approach because radiation levels were still too high for construction directly over the damaged reactor. The NSC is designed to last for 100 years and includes sophisticated ventilation systems, radiation monitoring equipment, and remote control cranes that will eventually be used to dismantle the old sarcophagus and remove the radioactive materials inside. However, even this impressive feat of engineering is merely buying time, not solving the fundamental problem. Inside the NSC and the old sarcophagus lies approximately 200 tons of nuclear fuel and radioactive materials in various forms. Some of this material has formed into strange, highly radioactive structures known as lava flows or corium, created when molten nuclear fuel mixed with concrete, sand, and other materials during the meltdown. The most famous of these formations is the Elephant's Foot, a mass of corium discovered in the basement of the reactor building that was so radioactive it could deliver a lethal dose of radiation in just minutes of exposure. This material is slowly degrading and turning into radioactive dust. Studies have shown that the fuel-containing materials are gradually disintegrating due to radiation damage, oxidation, and interaction with water that seeps into the structure. This process creates fine radioactive particles that could become airborne if the containment fails. The current plan is to use the NSC as a workspace to eventually dismantle the sarcophagus and remove the radioactive materials, but this presents enormous technical challenges. No one has ever attempted to clean up a disaster of this scale before. The radiation levels inside remain extremely high, making direct human intervention impossible for extended periods. Robots and remote-controlled equipment will need to be developed that can function in the intense radiation environment, which damages electronics and mechanical systems. The radioactive materials will need to be carefully removed, packaged, and stored somewhere safe for thousands of years. Current estimates suggest this cleanup process could take 50 to 100 years and cost tens of billions of dollars. Even after the cleanup is complete, the question remains: where do you safely store highly radioactive nuclear waste that will remain dangerous for millennia? This brings us to one of the most troubling aspects of Chernobyl's legacy: the problem of long-term nuclear waste storage, and the burden we are placing on future generations who will inherit this radioactive legacy but had no say in creating it. One of the most eerie and scientifically fascinating aspects of the Chernobyl disaster is what happened to the forest immediately surrounding the reactor. In the days following the explosion, a pine forest located directly downwind from the reactor turned a striking reddish-brown color as the trees absorbed massive doses of radiation and died. This area, covering approximately 4 square kilometers, became known as the Red Forest, and remains one of the most radioactively contaminated areas on Earth. The trees absorbed so much radiation that they themselves became radioactive, glowing eerily in photographs taken with radiation-sensitive cameras. Soviet authorities eventually bulldozed much of the Red Forest and buried the contaminated trees in trenches, but this merely buried the problem rather than solving it. Today, new vegetation has grown in the Red Forest, but the soil remains heavily contaminated with radioactive isotopes that continue to be absorbed by plants and trees. What scientists have discovered about the Red Forest and the broader Chernobyl Exclusion Zone forests is deeply troubling for long-term environmental contamination. In normal forests, dead plant material decomposes relatively quickly, broken down by bacteria, fungi, and insects in a process that recycles nutrients back into the soil. However, in the highly radioactive environment of Chernobyl, this decomposition process has been dramatically slowed. Studies have found that leaf litter and dead wood in the most contaminated areas decompose 40% slower than in uncontaminated forests. This is because the radiation has damaged or killed many of the microorganisms responsible for decomposition. As a result, decades worth of dead, radioactive plant material has accumulated on the forest floor, creating an enormous store of radioactive fuel that poses a catastrophic wildfire risk. Forest fires have become one of the most serious pathways for spreading Chernobyl's radioactive contamination beyond the exclusion zone. When fires sweep through the contaminated forests, they release radioactive particles that have been locked in vegetation and soil back into the atmosphere. These particles can then be carried by wind over long distances, potentially recontaminating areas that have been cleaned or contaminating previously unaffected regions. In April 2020, a series of wildfires burned through large areas of the exclusion zone, coming within a few kilometers of the reactor site itself and the radioactive waste storage facilities. Air quality monitors in Kyiv, about 100 kilometers from Chernobyl, detected elevated levels of radiation during these fires. Scientists have calculated that a major fire in the most contaminated areas could release amounts of cesium, 137 comparable to what was released during the initial disaster. Climate change is making the situation considerably worse. The region around Chernobyl is experiencing hotter, drier summers that increase wildfire risk. Studies project that the frequency and intensity of forest fires in the exclusion zone will increase significantly in coming decades as the climate warms. This creates a disturbing positive feedback loop. Fires release radioactive particles into the atmosphere, and the radioactive contamination of the forest makes the fires more difficult to fight because firefighters and equipment cannot safely enter the most contaminated areas. The Ukrainian authorities have limited resources to monitor and fight fires in the vast exclusion zone, which covers 2,600 square kilometers. The situation has been further complicated by the Russian invasion of Ukraine that began in 2022, which saw military operations conducted in and around the exclusion zone, including the occupation of the Chernobyl site itself for several weeks. The movement of military vehicles to the zone stirred up radioactive dust and created new fire risks. The forests of the Chernobyl exclusion zone have essentially become vast radioactive reservoirs that will continue to pose contamination risks for generations to come. The radioactive isotopes in the soil have been absorbed by trees and plants that will eventually die and decompose or burn in wildfires, releasing contamination back into the environment in an endless cycle. Some of these isotopes, particularly cesium, 137 and strontium, 90, will remain dangerous for hundreds of years. Even more concerning are the longer-lived isotopes like plutonium, 239 and americium, 241, which will remain hazardous for tens of thousands of years. The trees and vegetation growing in the zone today are absorbing these isotopes from the soil, effectively concentrating the radioactivity in biological materials that can burn and disperse contamination. Future generations will need to monitor and manage these contaminated forests for centuries, fighting fires, restricting access, and dealing with periodic releases of radioactive materials. This represents an environmental management challenge unlike any faced before, requiring sustained effort and resources far into the future to protect populations from a disaster that occurred decades or even centuries earlier. While much attention is focused on airborne radiation and contaminated soil, one of the most insidious and long-lasting threats from Chernobyl is the contamination of water systems. In the immediate aftermath of the disaster, enormous quantities of radioactive materials settled on the ground across a vast area of Ukraine, Belarus, and Russia. Rain and snowmelt began washing these contaminants into rivers, streams, lakes, and underground aquifers. The Pripyat River, which flows directly past the Chernobyl plant, became heavily contaminated and carries radioactive materials into the Dnieper River, one of the major river systems of Eastern Europe. The Dnieper provides drinking water for millions of people in Ukraine, including the capital city of Kyiv. In the weeks and months following the disaster, authorities had to take emergency measures to prevent heavily contaminated water from reaching downstream populations. The behavior of radioactive contaminants in water systems is complex and, in many ways, more dangerous than airborne contamination. When radioactive particles settle in sediments at the bottom of rivers and lakes, they are not permanently fixed in place. During floods, storms, or seasonal high water events, these sediments can be stirred up and transported downstream, recontaminating areas that have been cleaned or spreading contamination to new areas. Studies of the Pripyat River system have found that radioactive cesium-137 continues to be detected in river sediments at levels that pose health risks decades after the initial contamination. Some radioactive isotopes, particularly strontium-90, are water-soluble and can travel long distances in groundwater. This creates a hidden contamination pathway that is difficult to monitor and control. Groundwater contamination presents particularly serious long-term risks. The damaged Reactor 4 and the various waste storage facilities in the Exclusion Zone sit atop aquifers that are part of larger groundwater systems. Rainwater and snowmelt percolate down to the contaminated soil and structures, picking up radioactive materials and carrying them into the groundwater. Once in the groundwater, these contaminants can travel considerable distances, potentially reaching wells, rivers, and water supplies far from the exclusion zone. Modeling studies have shown that a plume of radioactive contamination is slowly spreading to the groundwater beneath Chernobyl. The speed of this contamination spread is difficult to predict because it depends on complex geological factors, including soil composition, groundwater flow rates, and chemical interactions between the radioactive materials and minerals in the soil. One of the most alarming discoveries in recent years is that some radioactive contaminants are being transported through the environment in unexpected ways. Research has shown that certain bacteria and fungi can actually concentrate radioactive isotopes from their environment. These microorganisms absorb radioactive elements and incorporate them into their cellular structures. When these microorganisms are consumed by larger organisms, or when they die and decompose, the radioactive materials can be released in more mobile or bioavailable forms. This biological concentration and transport radioactivity creates pathways for contamination to spread that were not initially anticipated by scientists. Fish in the Pripyat River and its tributaries, for example, have been found to contain levels of cesium-137 that are hundreds of times higher than the water they swim in, demonstrating how biological organisms can concentrate radioactive materials. The challenge of water contamination at Chernobyl will persist for generations. The radioactive source materials in and around the damaged reactor will continue to leach contaminants into the environment for decades or centuries. Climate change is likely to exacerbate these problems by altering precipitation patterns and potentially increasing flooding events that can mobilize contaminated sediments. Future generations will need to maintain constant monitoring of water systems in and around the exclusion zone. They will need to be prepared to implement emergency measures if contamination levels spike, and they will need to restrict access to water sources that remain unsafe. Perhaps most concerning is that much of the groundwater contamination is occurring slowly and invisibly, creating a hidden threat that will not become fully apparent for decades, but will be very difficult to remediate once the contamination has spread through vast underground aquifer systems. The burden of monitoring and managing this water contamination will fall on people who were not born when the disaster occurred, yet will spend their entire lives dealing with its consequences. One of the great ironies of the Chernobyl disaster is that the exclusion zone, created to protect humans from deadly radiation, has become a thriving wildlife sanctuary. In the absence of human habitation activity, populations of wolves, wild boar, deer, elk, lynx, bears, and even highly endangered species like the European bison and Przewalski's horse have flourished. Camera traps and wildlife surveys have documented an abundance of wildlife that far exceeds what was present before the disaster. This has led to what some call the Chernobyl paradox, the demonstration that human activity is often more damaging to wildlife than even a major nuclear disaster. However, this seemingly positive outcome masks a darker reality about the effects of chronic radiation exposure on living organisms and what it might mean for future generations. Scientific studies of Chernobyl's wildlife have revealed that animals living in the most contaminated areas show clear signs of radiation damage. Birds in high radiation zones have been found to have smaller brains, impaired cognitive abilities, higher rates of tumors and cataracts, reduced fertility, and shorter lifespans compared to birds from uncontaminated areas. Insects show elevated rates of developmental abnormalities, with some studies finding that up to 30% of insects in the most contaminated areas display visible mutations. Bank voles and other small mammals living in radioactive hotspots have been found to have damaged DNA, increased oxidation stress, compromised immune systems, and higher cancer rates. These effects are not universal across all species or all areas of the exclusion zone, creating a complex picture of how radiation affects different organisms in different ways. Perhaps most concerning from a long-term perspective is evidence that radiation is causing heritable genetic mutations in some Chernobyl wildlife populations. Studies of dogs living in and around the exclusion zone have found that these populations have developed unique genetic signatures not found in dog populations elsewhere. Genetic analysis shows elevated mutation rates and evidence of rapid evolutionary changes as the dog populations adapt to the radioactive environment. Similar genetic changes have been documented in other species, including mice, birds, and even trees. Some organisms appear to be developing increased radiation tolerance through selection pressure. Individuals with genetic variations that provide some protection against radiation damage are more likely to survive and reproduce, gradually increasing the frequency of these protective genetic traits in the population. While this sounds like a success story of adaptation, it raises troubling questions about what other changes these mutations might be causing and whether this rapid genetic change could have unforeseen negative consequences. The wildlife of Chernobyl essentially serves as a long-term experiment in the effects of chronic, multi-generational radiation exposure. What scientists are learning has profound implications for understanding how radiation affects biological systems over extended time periods. One key finding is that different species show dramatically different susceptibilities to radiation. Some species, particularly certain bacteria, fungi, insects, and even some plants, appear relatively unaffected even in highly contaminated areas. Others, especially birds and mammals with complex development and long lifespans, show clear negative effects. Interestingly, some organisms appear to be thriving in the contaminated environment, possibly because they have developed protective mechanisms or because the absence of human disturbance more than compensates for the radiation stress. However, the question remains, what are the long-term implications of these genetic changes for the wildlife populations and ecosystems at Chernobyl? Studies have found that radiation can affect organisms across multiple generations, even when later generations are not directly exposed to high radiation levels. This suggests that genetic damage caused by radiation can be inherited and potentially accumulate over time. While research on humans who were exposed to Chernobyl radiation has not found evidence of heritable genetic effects in their children, this may be because humans have longer generation times and better DNA repair mechanisms than many other organisms. The wildlife data suggests we cannot be entirely certain that multi-generational exposure to even relatively low levels of radiation is completely safe. Furthermore, the animals of Chernobyl are not confined to the exclusion zone. Wolves, deer, wild boar, and birds regularly move across the zone boundaries, potentially carrying both radioactive contamination and radiation-induced genetic mutations into populations outside the zone. This creates another pathway by which Chernobyl's legacy can spread to affect broader populations and ecosystems, a subtle but potentially significant impact that will continue for generations as these animals migrate and interbreed with populations far from the disaster site. One of the most emotionally charged and scientifically complex questions surrounding Chernobyl is whether radiation exposure caused genetic damage that could be passed to future generations. In the aftermath of the disaster, hundreds of thousands of people were exposed to significant levels of radiation. These included the emergency workers and liquidators who responded to the disaster, residents of heavily contaminated areas who were not evacuated immediately, and people who continue to live in less contaminated regions. Concerns arose that this radiation exposure might cause mutations in egg and sperm cells that could be inherited by children, potentially causing birth defects, genetic diseases, and health problems in generations not yet born. This fear was not unfounded. Studies of Japanese atomic bomb survivors had suggested possible increases in genetic abnormalities in their descendants, though the evidence was not conclusive. Recent comprehensive genetic studies of Chernobyl survivors and their children have provided some reassuring news. Researchers have not found evidence that radiation exposure caused inherited genetic changes in the children of exposed parents. A major study published in 2021 examined the complete genomes of 130 children born to 105 couples where at least one parent was exposed to Chernobyl radiation. The researchers look for de novo mutations, genetic changes that appear in children but are not present in either parent, which would indicate new mutations caused by radiation damage to parental reproductive cells. The study found no increase in these de novo mutations in children of exposed parents compared to the general population. This suggests that even significant radiation exposure does not necessarily cause heritable genetic damage in humans, at least not at levels that can be detected with current technology. However, scientists caution that this relatively reassuring finding does not mean we can completely dismiss concerns about potential genetic effects. First, the studies have limitations in terms of sample size and the types of genetic changes they can detect. It is possible that there are subtle genetic effects that would only become apparent in larger populations or across multiple generations. Second, the exposed populations are still relatively young in generational terms. Most children of exposed parents are only in their 30s or 40s. If radiation caused genetic changes that increase disease susceptibility later in life, these effects might not become apparent until these individuals reach old age. Third, some types of genetic damage might not cause obvious disease, but could have subtle effects on health, longevity, or disease susceptibility that are difficult to detect without very large-scale, long-term studies. Furthermore, while the genetic studies focus on inherited mutations, radiation is known to cause other biological changes that could affect health across generations. Radiation can cause epigenetic changes, alterations in how genes are expressed without changing the underlying DNA sequence. These epigenetic modifications can potentially be passed to children and might influence disease risk. Research is ongoing to determine whether Chernobyl radiation exposure caused inheritable epigenetic changes and what effects these might have. Additionally, radiation exposure can damage the cellular machinery responsible for DNA repair and cell division. If these systems are compromised in ways that can be inherited, it might increase the mutation rate in subsequent generations even if the initial radiation exposure did not directly cause inherited mutations. The question of genetic effects takes on particular significance when we consider the scale of exposure. It is estimated that over 600,000 people were significantly exposed to Chernobyl radiation, including liquidators, evacuees, and residents of contaminated areas. Millions more received lower but still elevated exposures. Even if the risk of genetic damage to any individual is small, when applied across such large populations, there could be significant numbers of people affected. Moreover, the populations living in and around the exclusion zone continue to be exposed to elevated radiation levels from contaminated food, water, and environmental sources. This ongoing chronic exposure creates a different risk profile than the acute exposures that have been most studied. The full impact of chronic, multi-generational radiation exposure on human genetics may not become clear for decades or even centuries. Future generations will need to maintain long-term health monitoring of populations descended from exposed individuals to watch for any delayed or multi-generational effects. The absence of evidence for genetic damage in the current generation is encouraging, but is not proof that such effects cannot or will not occur in future generations, particularly as these populations continue to live in an environment where low-level radiation exposure is ongoing. The most well-documented health impact of the Chernobyl disaster is a dramatic increase in thyroid cancer, particularly among people who were children at the time of the accident. In the days immediately following the explosion, huge quantities of radioactive iodine, 131, were released into the atmosphere. This isotope has a relatively short half-life of just 8 days, meaning it decays quickly, but in those initial days and weeks, it contaminated grass and other vegetation that was eaten by cows. The radioactive iodine concentrated in cow's milk, which was consumed by children in large quantities. The human thyroid gland avidly absorbs iodine to produce thyroid hormones, and children's thyroid glands are particularly active. As a result, thousands of children in Ukraine, Belarus, and Russia absorbed radioactive iodine into their thyroid glands, receiving significant radiation doses to this small but crucial organ. The consequences have been devastating. In the regions most affected by Chernobyl fallout, thyroid cancer rates in people who were children at the time of the accident increased by factors of 10 to 100 compared to pre-disaster levels. By some estimates, more than 5,000 cases of thyroid cancer can be directly attributed to Chernobyl radiation exposure, and this number continues to increase as exposed individuals age. The increase was first noticed in the early 1990s, about 5 years after the disaster, and rates have remained elevated ever since. Fortunately, thyroid cancer is generally highly treatable if caught early, and the majority of patients survive, but they require lifelong medical monitoring and often need to take thyroid hormone replacement medication for the rest of their lives. This represents a massive burden on healthcare systems in affected regions and a lifelong impact on the health and quality of life of survivors. The question of other cancers is more controversial and uncertain. Studies have suggested increases in leukemia, breast cancer, and other solid tumors in exposed populations, but the evidence is less clear-cut than for thyroid cancer. This is partly because these cancers have multiple causes and occur at background rates in all populations, making it statistically difficult to detect increases unless they are very large. It typically takes decades for radiation-induced cancers to develop, and we are only now, nearly 40 years after disaster, entering the period when we would expect to see peak rates of solid tumors in exposed populations. Some studies have found elevated rates of leukemia in liquidators who receive high radiation doses. Research has also suggested possible increases in breast cancer in women who were young girls at the time of exposure. However, other studies have not found clear evidence of increases in these cancers. The difficulty in assessing the true cancer burden from Chernobyl is complicated by several factors. First, the Soviet government's initial cover-up and inadequate record-keeping means we do not have accurate data on how much radiation individual people received. Second, the affected populations have faced many other health challenges, including poverty, poor diet, stress, smoking, and alcohol abuse that also increase cancer risk, making it difficult to separate radiation effects from these other factors. Third, increased medical surveillance of exposed populations means cancers are more likely to be detected even if radiation did not cause them, potentially creating an apparent increase that is really just better detection. Despite these uncertainties, most scientific bodies estimate that Chernobyl radiation will eventually cause between 4,000 and 93,000 additional cancer deaths, with a wide range reflecting the different assumptions and methodologies used in risk calculations. What makes the cancer legacy at Chernobyl particularly troubling for future generations is that the risk is not over. People who were exposed as children in 1986 are now in their 40s and 50s, approaching the age when cancer rates naturally increase. We can expect to see continuing increases in cancer diagnoses in this population for decades to come. Furthermore, people continue to live in contaminated areas and receive ongoing low-level radiation exposure from food, water, and the environment. While the doses are much lower than in the immediate aftermath of the disaster, this chronic exposure over entire lifetimes could produce health effects that are difficult to predict. Children born years or even decades after the disaster, but growing up in contaminated regions, are receiving cumulative radiation doses that could increase their cancer risk. Future generations will need to maintain cancer registries and health monitoring programs for populations in affected regions for the foreseeable future. The true full cancer toll of Chernobyl will not be known for many decades and may not be fully realized until current generations have lived out their entire lives. While physical health effects from radiation are the most obvious concern, one of the most pervasive and underestimated impacts of the Chernobyl disaster has been on mental health and psychological well-being. A 2005 report by the UN Chernobyl Forum identified mental health problems as the largest public health problem unleashed by the accident. This might seem surprising given the cancer increases and other physical health effects, but the psychological impact has affected far more people and in many ways has been more debilitating than the physical health consequences for most of the exposed population. The disaster created a pervasive sense of fear, helplessness, and victimization among affected populations that persists decades later. The sources of psychological trauma are multiple and interconnected. First, there's a fear of radiation itself, an invisible, odorless, tasteless threat that could be anywhere and that might be causing harm to oneself and one's children without any immediate warning. This fear has been exacerbated by conflicting information about radiation risks, with some sources downplaying the dangers while others present catastrophic scenarios. Second, many people were forcibly evacuated from their homes, often with little warning and no ability to return. The city of Pripyat, home to nearly 50,000 people, was completely abandoned within 36 hours of the disaster, and residents have never been allowed to return permanently. Entire villages across Ukraine and Belarus were bulldozed and buried after being deemed too contaminated for habitation. The loss of home, community, and sense of place has a profound and lasting effects on evacuees. Third, there is the stigmatization of Chernobyl victims. People from contaminated regions report being treated as if they are themselves contaminated or diseased. Some have experienced discrimination in employment, education, and even marriage, as potential partners fear that radiation exposure might cause genetic defects in children. This stigma has led to feelings of shame and social isolation that compound the other stresses faced by affected populations. Fourth, there are the socioeconomic impacts. The disaster and subsequent collapse of the Soviet Union devastated the economies of affected regions. Many people who lost homes and livelihoods have lived in poverty for decades, dependent on inadequate government compensation, and struggling with unemployment and lack of economic opportunities. Studies have documented high rates of anxiety, depression, post-traumatic stress disorder, and psychosomatic illnesses in affected populations. One particularly troubling phenomenon is what researchers call paralyzing fatalism, a sense that one's fate is controlled by external forces, and that any effort to improve one's situation is futile. This learned helplessness has led many people to adopt unhealthy behaviors, such as heavy drinking and smoking, reasoning that if radiation is going to kill them anyway, there is no point in trying to stay healthy. This, ironically, may be causing more health problems than the radiation itself for many people in affected areas. The mental health legacy of Chernobyl extends across generations. Children born after the disaster to parents who have grown up in households marked by anxiety, fear, and economic hardship. They have been taught to fear an invisible threat and have internalized the sense of victimhood and fatalism of their parents. Studies have found elevated rates of anxiety and depression in young people in affected regions who have no personal memory of the disaster but have been profoundly shaped by its aftermath. This intergenerational transmission of trauma represents a hidden cost of the disaster that is difficult to quantify, but very real in its impact on millions of lives. Future generations will continue to grapple with this psychological legacy. Even as physical health risks diminish over time as radioactive isotopes decay, the psychological and social impacts may persist, passed down through families and communities as a form of collective trauma. Addressing this will require not just medical monitoring, but sustained mental health support, community rebuilding efforts, and social programs to address poverty and lack of opportunity in affected regions. The Chernobyl disaster represents not only a human and environmental catastrophe, but also an economic burden of staggering proportions that will weigh on future generations for decades to come. In the immediate aftermath, the Soviet Union spent billions of rubles on emergency response, evacuations, medical care for victims, and construction of the sarcophagus. The exact costs are difficult to calculate due to poor record-keeping and the subsequent collapse of the Soviet Union, but estimates suggest the initial response cost the equivalent of tens of billions of dollars in today's money. This was a devastating blow to an economy that was already struggling and contributed to the Soviet Union's eventual collapse. After the breakup of the Soviet Union, the newly independent states of Ukraine and Belarus inherited the majority of the costs associated with Chernobyl. These included ongoing medical care for hundreds of thousands of affected people, compensation payments to evacuees and liquidators, environmental monitoring and remediation, management of the exclusion zone, and maintenance of the sarcophagus. For Ukraine, Chernobyl-related expenses consumed up to 15% of the national budget in some years during the 1990s. For Belarus, which received about 60% of the Chernobyl fallout despite not hosting the reactor, the costs have been similarly crippling, consuming 10 to 20% of the national budget in some years. These are enormous burdens for countries that were already economically devastated by the transition from communism to market economies. The construction of a new safe confinement, completed in 2016, cost approximately 1.5 billion euros and was funded primarily by international donors through the Chernobyl Shelter Fund. However, this is just one component of the long-term costs. The NSC itself requires ongoing maintenance and monitoring, estimated to cost tens of millions of euros annually. The eventual dismantling of the sarcophagus and removal of the radioactive materials, which must occur within the 100-year design life of the NSC, is expected to cost tens of billions of dollars. Where this money will come from is an open question, as international donor interest has waned and Ukraine faces many other pressing economic challenges. Beyond the direct costs of managing the disaster site, there are the ongoing costs of healthcare, environmental monitoring, food safety testing, and social support for affected populations. Thousands of people require long-term medical care for radiation-related illnesses. Extensive areas of agricultural land remain contaminated and cannot be used for food production, representing a permanent loss of economic productivity. Food produced in less contaminated but still affected areas must be carefully monitored to ensure radioactive contamination levels are within acceptable limits, requiring sophisticated testing infrastructure. The exclusion zone itself represents a massive loss of productive land, 2,600 square kilometers that could otherwise support agriculture, forestry, and human habitation. There are also enormous opportunity costs. Resources that go to managing Chernobyl's legacy cannot be used for other purposes such as education, infrastructure development, or healthcare improvements. For Ukraine and Belarus, two of Europe's poorest countries, this has meant sacrificing potential investments that could have improved living standards and economic development. Some economists have estimated the total economic cost of Chernobyl to Ukraine and Belarus over the first 30 years after the disaster at over $700 billion. If we project these costs forward over the centuries that radioactive contamination will persist, the ultimate economic burden becomes almost incomprehensible. Future generations will inherit not just radioactive contamination, but the massive financial obligations that come with managing it. They will need to fund decommissioning work, maintain containment structures, monitor environmental contamination, provide health care to affected populations, and manage vast areas of contaminated land. All of this to address a disaster they had no role in creating, caused by decisions made decades or centuries earlier. This represents a profound intergenerational injustice. The transfer of massive costs and risks from the generations that benefited from nuclear power to future generations who will bear the burdens but receive none of the benefits. One of the most underappreciated aspects of Chernobyl's long-term risk is how climate change is fundamentally altering the nature of the contamination threat. When scientists initially assessed the risks posed by Chernobyl's radioactive contamination, they did so based on the assumption that environmental conditions would remain relatively stable. Radioactive isotopes would gradually decay to safe levels following predictable physical laws, and contamination would slowly be diluted and dispersed through natural processes. However, climate change is disrupting these assumptions by creating environmental conditions that can remobilize and redistribute contamination in ways that were not originally anticipated. Rising temperatures and changing precipitation patterns are increasing the frequency and severity of wildfires in the exclusion zone. As discussed earlier, these fires can release large quantities of radioactive particles that were locked in vegetation and soil back into the atmosphere. Climate projections suggest that the region around Chernobyl will experience hotter, drier summers with increased drought risk, creating conditions highly favorable for large wildfires. A major study examining fire risk in exclusion zone projected that the area burned by wildfires could increase by 300 to 400% by the end of this century under likely climate change scenarios. This would create recurring contamination events, with radioactive particles being released into the atmosphere every few years during major fires. Climate change is also affecting water systems in ways that could increase contamination risks. Changes in precipitation patterns can alter river flow regimes, potentially increasing flooding events that mobilize contaminated sediments and spread contamination to new areas. Extended droughts can concentrate contaminants and reduce water volumes, temporarily increasing contamination levels in water sources. Rising temperatures can affect the behavior of radioactive materials in the environment, potentially increasing their mobility or bioavailability. Warmer water temperatures can change the chemistry of rivers and lakes in ways that affect how radioactive contaminants behave, potentially making them more likely to be absorbed by organisms or transported through aquatic systems. The biological impacts of climate change compound radiation risks in complex ways. Climate change is already causing shifts in the distributions and behaviors of plant and animal species. In the Chernobyl region, this could mean that species move into or out of contaminated areas in response to changing temperatures and habitat conditions. Species that move into contaminated areas will be exposed to radiation and could serve as vectors for spreading contamination to new areas. Climate-induced stress on ecosystems can make organisms more vulnerable to other stressors, including radiation, potentially increasing the biological impacts of contamination. For example, if climate change causes food shortages, animals may be forced to feed in more contaminated areas than they otherwise would, increasing their radiation exposure. Perhaps most concerning is that climate change creates fundamental uncertainties in long-term risk assessments. All of the models and predictions about how Chernobyl's contamination will behave over coming decades and centuries were developed based on historical climate conditions. If climate change creates novel environmental conditions with no historical precedent, these predictions may be wrong. We may discover new pathways for contamination spread or find that radioactive materials persist in the environment longer than expected if climate change alters the physical, chemical, and biological processes that break down and disperse contaminants. Future generations will face the challenge of managing Chernobyl's radioactive legacy in a climate that is significantly different from the one in which the disaster occurred. They will need to develop new strategies and technologies to address contamination risks that emerge under novel environmental conditions. The interaction between long-lived radioactive contamination and a rapidly changing climate represents an unprecedented challenge, one that will require sustained effort and adaptation for generations to come. While Chernobyl occurred in Ukraine, its implications extend far beyond national or even regional boundaries. The disaster released radioactive contamination that spread across much of Europe and parts of Asia. Within days of the explosion, elevated radiation levels were detected in Sweden, over 1,000 kilometers away. Within weeks, contamination had been measured across most of Europe, from Scandinavia to the Mediterranean. Some areas far from Chernobyl, such as parts of Norway, Sweden, Scotland, Wales, and even northern Italy, received surprisingly high levels of contamination due to particular weather patterns at the time of the disaster, and because rain fell while contaminated air masses were passing over, washing radioactive particles out of the atmosphere. The global distribution of Chernobyl contamination revealed the terrifying reality that nuclear accidents cannot be contained within national borders. Radioactive materials released into the atmosphere can travel thousands of kilometers and contaminate countries that had no role in the accident and no benefit from the nuclear facility that caused it. This created complex international liability and compensation issues. Countries affected by Chernobyl fallout face costs for monitoring contamination, testing food supplies, restricting use of contaminated agricultural products, and providing health monitoring for their populations. Who should bear these costs? The country where the accident occurred? The international community? These questions were largely left unresolved. Chernobyl also transformed the global nuclear industry and public perception of nuclear power. Before Chernobyl, nuclear power was seen by many as a relatively safe, clean source of electricity that would play a major role in meeting future energy needs. Chernobyl shattered this perception, demonstrating that nuclear accidents, while rare, could have truly catastrophic consequences that persist for generations. The disaster triggered a wave of anti-nuclear sentiment, particularly in Europe, that led to the cancellation of nuclear plant construction projects and the eventual phase-out of nuclear power in some countries, including Italy, Austria, and Germany. This represented a major shift in energy policy with implications for global efforts to address climate change, as nuclear power is a low-carbon energy source that could have played a larger role in replacing fossil fuels. The lessons of Chernobyl extend beyond nuclear power to questions about technological risks, governance, and intergenerational responsibility. Chernobyl demonstrated how failures in safety culture, inadequate regulation, and secrecy can turn technological systems into disasters. The Soviet government's initial cover-up and delayed response undoubtedly made the disaster worse and increased exposure for both Soviet citizens and people in other countries. This highlighted the need for transparency and international cooperation in managing nuclear risks. The disaster also raised profound questions about whether it is ethical to create technologies that generate waste and contamination that will remain dangerous for thousands of years, effectively imposing risks and costs on countless future generations. What right do we have to burden our descendants with problems that will persist long after any benefits have been exhausted? Chernobyl provides a stark case study of how decisions made by one generation can profoundly impact the lives and choices available to many subsequent generations. The people who designed, built, and operated the Chernobyl nuclear plant are mostly dead, yet the contamination they release will persist for centuries, requiring management, monitoring, and resources from generations not yet born. This represents a fundamental challenge to how we think about responsibility and justice across time. As we face other long-term challenges such as climate change, nuclear waste disposal, and biodiversity loss, Chernobyl offers sobering lessons about the long shadows that current decisions can cast. It reminds us that we are not isolated in time but connected across generations, and that our actions today will shape the world inherited by our descendants in ways we may not fully anticipate or understand. While the Chernobyl Exclusion Zone receives considerable attention, there are vast areas of contaminated land outside the zone that pose ongoing risks but receive far less monitoring and management. The radioactive plume from Chernobyl spread contamination over approximately 150,000 square kilometers across Ukraine, Belarus, and Russia. The exclusion zone itself covers only 2,600 square kilometers, leaving enormous areas that are contaminated to varying degrees, but where people continue to live, work, and farm. These areas, sometimes called the Zone of Obligatory Resettlement or Zone of Enhanced Radiological Control, are home to millions of people who receive ongoing radiation exposure from their environment. In many of these areas, contamination is patchy and unpredictable. One field might be relatively clean while the neighboring field, which received rain at the time contaminated air masses passed over, could have contamination levels many times higher. This creates a complex landscape of hotspots and clean areas that is difficult to map and manage. Many residents, particularly in rural areas, depend on locally produced food, including milk, meat, mushrooms, berries, and fish that can contain elevated levels of radioactive contamination. While governments have established safety limits and monitoring programs, enforcement is inconsistent, particularly in remote areas. Studies have found that people in some contaminated regions continue to consume food with contamination levels above recommended limits, either because they are unaware of the risks, because they have no alternatives, or because they simply do not believe the official warnings. The economic and social impacts on the forgotten contaminated regions have been severe. Agricultural land contamination has destroyed the livelihoods of farming communities. Timber from contaminated forests cannot be sold, devastating the forestry industry in affected regions. These areas have experienced significant outmigration as younger, more mobile residents leave for cleaner areas with better economic opportunities, leaving behind aging populations with higher health needs. The areas have become pockets of poverty and neglect, sometimes called Chernobyl ghettos, where residents feel abandoned by their governments and stigmatized by outsiders. As time passes and memories of the disaster fade, there's a risk that contaminated areas outside the exclusion zone will be increasingly forgotten and neglected. Younger generations of government officials and policymakers may lack awareness of contamination issues. Economic pressures may lead to rollbacks in monitoring and safety programs. People may resettle contaminated areas unaware of the risks, particularly if economic conditions elsewhere are poor. Already there are reports of people illegally living in the exclusion zone itself, either because they refuse to leave their ancestral homes or because they have nowhere else to go. This forgetting of contamination creates risks that problems will reemerge in unexpected ways. Future generations will need to maintain institutional memory and ongoing management of these contaminated regions for decades or centuries. This is extraordinarily challenging. How do you ensure that people hundreds of years from now remember that certain areas are contaminated and should be avoided or carefully managed? Human societies have no experience with managing environmental hazards that persist for such timescales. The longest-lasting human institutions, such as certain religious organizations, are only a few thousand years old, and even they have gone through periods of disruption and loss of knowledge. Archaeologists studying how to mark nuclear waste storage sites to warn future civilizations have concluded that ensuring warning messages remain understandable for 10,000 years or more is extraordinarily difficult, if not impossible. The contaminated lands at Chernobyl present a similar challenge on a larger geographic scale. How do we ensure that future societies remember and appropriately manage these lands long after everyone alive at the time of the disaster is dead and the political and social structures of our time may have changed beyond recognition? The Chernobyl disaster has generated enormous quantities of radioactive waste that must be safely managed for centuries or millennia. This includes the fuel and radioactive materials in the damaged reactor, the old sarcophagus structure itself, which is now radioactive, contaminated equipment and debris, contaminated soil that has been excavated from cleanup sites, contaminated buildings that must eventually be demolished, and even the bodies of trees from the red forest that were buried in trenches. The scale of this waste problem is staggering. The Reactor complex, a major radioactive waste storage facility at the Chernobyl site that began operations in 2008, is designed to eventually hold approximately 21,000 spent nuclear fuel rods, many of them damaged, plus enormous quantities of other radioactive materials. Additional facilities are being constructed to process and store the various types of radioactive waste generated by the disaster and the ongoing cleanup efforts. In 2025, Ukraine received approval to begin operations at the industrial complex for solid radioactive waste management, a facility that will process and store radioactive waste for the next 30 years. This complex includes multiple facilities integrated into a single technology cycle, temporary storage for various waste types, retrieval systems for existing waste, sorting and processing facilities that can incinerate and cement contaminated materials, and near-surface storage designed to hold 55,000 cubic meters of low and intermediate-level waste for 300 years. The fact that this facility is designed to store waste for 300 years, more than a dozen generations into the future, illustrates the time scales involved in managing Chernobyl's radioactive legacy. And this is just for the lower-level waste. The high-level waste, including the reactor fuel, will require storage for thousands of years. The decommissioning timeline for Chernobyl reveals the multi-generational nature of this challenge. The 3 intact reactors at Chernobyl continued operating for years after the disaster, with Reactor 3 not shutting down until 2000. The decommissioning process for these reactors is expected to follow a phased approach, final shutdown and preservation taking up to 10 years, followed by a safe enclosure period lasting approximately 100 years to allow radiation levels to decrease, and finally dismantling taking another 8 to 10 years. As for Reactor 4, the damaged reactor at the center of the disaster, estimates suggest it will remain highly radioactive for up to 20,000 years. Some experts predict that the new safe confinement structure itself may need to be replaced within 30 years depending on conditions, as the area cannot be truly cleaned, only contained. This raises a fundamental question that extends far beyond Chernobyl: how we safely store radioactive waste that will remain dangerous for timescales that dwarf human history. Worldwide, more than 250,000 metric tons of highly radioactive waste sits in storage near nuclear power plants and weapons production facilities, with over 90,000 metric tons in the United States alone. None of this waste has yet been placed in permanent disposal facilities. The prevailing international consensus is that high-level nuclear waste should eventually be placed in deep geological repositories, buried hundreds or thousands of meters underground in stable rock formations. The idea is that geological barriers combined with engineered barriers like corrosion-resistant containers will isolate the radioactivity until it decays to safe levels. However, this solution faces enormous technical, political, and ethical challenges. Geologically stable sites are difficult to find, and local communities typically oppose having nuclear waste repositories in their areas. The containers must resist corrosion for thousands of years, a requirement that is difficult to test and guarantee. Underground water flows could corrode containers and transport radioactive materials through the environment in unpredictable ways. And fundamentally, we are making decisions about storage systems that must function correctly for longer than human civilization has existed. The pyramids of Egypt, among the oldest surviving human structures, are only about 4,500 years old. We are proposing to build facilities that must remain intact and function properly for 10 times that long or more. The financial implications are staggering. Estimating the cost of managing waste for thousands of years involves projecting expenditures for security, monitoring, and maintenance far into an uncertain future. Who will pay these costs? What institutions will be responsible for oversight? What happens if societies collapse, technologies are lost, or climate change fundamentally alters the geological and hydrological conditions at storage sites? These are questions that have no satisfactory answers. Yet there are burdens that current decisions about nuclear power and waste management are placing on countless future generations. One of the most philosophically profound challenges posed by Chernobyl and nuclear waste in general is the problem of communicating warnings across vast spans of time. How do we ensure that people living hundreds or thousands of years from now understand that certain areas are contaminated and dangerous? This might seem like a trivial problem at first consideration, but it becomes extraordinarily difficult when examined closely. Consider that the radioactive contamination at Chernobyl, particularly from long-lived isotopes like plutonium-239, with a half-life of 24,000 years, will remain dangerous far longer than any written language has existed. The oldest known writing systems, such as Sumerian cuneiform, are only about 5,000 years old, and most ancient languages cannot be read by modern people without specialized training. How can we create warning messages that will remain comprehensible to people living 10,000 or 20,000 years in the future, who may speak languages that don't exist yet and live in societies we cannot imagine? The U.S. Department of Energy has grappled with this problem in trying to design warning markers for the Waste Isolation Pilot Plant, a deep geological repository for nuclear waste in New Mexico. A panel of experts, including linguists, anthropologists, archaeologists, and artists, was assembled to propose solutions. They considered various approaches: massive earthworks that will remain visible for millennia, rooms full of warning messages in multiple languages, information encoded in durable materials like granite or ceramic, pictographic warnings that might be universally understood, and even the possibility of creating an atomic priesthood, a dedicated organization that would pass down warnings through an oral tradition lasting thousands of years. None of these solutions is entirely satisfactory. Earthworks could be eroded by climate change or misinterpreted as ceremonial monuments rather than warnings. Written messages may become incomprehensible. Pictographs might be misunderstood or ignored. And any human institution, even a dedicated priesthood, could fail or be disrupted over such vast timescales. The problem is not merely theoretical. History provides examples of how easily knowledge can be lost and warnings ignored. The ancient Romans used lead extensively in water pipes and cooking vessels, despite some observers noting that it caused health problems. This knowledge was lost in subsequent centuries, and lead continued to be used for similar purposes well into the 20th century, poisoning millions of people. Many archaeological sites contain unknown dangers. When Howard Carter opened Tutankhamun's tomb in 1922, he disregarded warnings and curses inscribed on the entrance, which may have been ancient Egyptians' attempts to warn future people about real dangers such as toxic molds or pathogens inside sealed tombs. More recently, there are documented cases of people in the former Soviet Union who found radioactive sources from abandoned equipment and, not understanding what they were, took them home, sometimes with fatal consequences. If people today can fail to recognize radioactive warnings despite having the language and technological knowledge to understand them, how much more difficult will it be for people thousands of years hence? The Chernobyl site itself presents this challenge in acute form. The exclusion zone is currently marked, fenced, and patrolled, with signs warning of radiation danger in multiple languages. But these are temporary measures that require ongoing maintenance and enforcement. The signs will deteriorate and need replacement. The fences will corrode. Most critically, the institutions responsible for maintaining the warnings and restrictions could fail if there is political collapse, economic crisis, or war in the region. The Russian invasion of Ukraine in 2022 demonstrated how vulnerable the Chernobyl site is to disruption. Russian forces occupied the area, and Ukrainian personnel were unable to carry out normal safety and monitoring activities for several weeks. If such disruptions occur during periods of social upheaval, knowledge about contamination could be lost, and future populations might resettle the area unaware of the dangers. Some have proposed radical solutions to the warning problem. One idea is to genetically engineer plants that change color in the presence of radiation, creating a living warning system that would persist as long as the contamination remains dangerous. Another proposal suggests deliberately making contaminated sites look repulsive or frightening through architecture and art, creating an instinctive aversion even if the specific danger is not understood. However, these approaches have their own problems. Engineered plants could evolve or be outcompeted by other species, and what one culture finds frightening or repulsive, another might find attractive or sacred. The fundamental challenge is that we are trying to communicate across a time span longer than any human cultural continuity has ever lasted. No language, religion, nation, or civilization has persisted for 10,000 years. Yet we are creating contamination that will persist for that long and longer, assuming responsibility for warnings that must somehow outlast all the institutions and cultures we know. This is perhaps the most profound burden we are placing on future generations. Not just the physical contamination itself, but the knowledge they will need to stay safe, knowledge that we have no reliable way to transmit across the vast gulf of time that separates us from them. The Chernobyl disaster forces us to confront difficult ethical questions about technology, risk, and our responsibilities to future generations. When we build nuclear power plants, we are making a trade-off. In exchange for several decades of electricity generation, we create radioactive waste and contamination that will persist for thousands of years. The benefits accrue to the current generation that uses electricity, while the costs and risks are largely borne by future generations who inherit the waste and contamination but receive none of the benefits. Is this ethical? Do we have the right to impose such burdens on our descendants? These questions become even more acute when we consider accidents like Chernobyl, where a single disaster creates contamination and suffering that will persist for centuries. Some argue that nuclear power is justified because it provides large amounts of low-carbon electricity, which is essential for addressing climate change. From this perspective, the risks of nuclear power, while real, are smaller than the catastrophic risks posed by continued reliance on fossil fuels. Burning coal, oil, and gas is causing climate change that threatens the entire planet and can make large areas uninhabitable, displace hundreds of millions of people, cause widespread ecosystem collapse, and fundamentally alter the conditions that have allowed human civilization to flourish. Compared to this existential threat, the localized contamination from nuclear accidents, terrible as it is, affects far fewer people. By this logic, we have an obligation to use nuclear power to avoid the even worse harm of unchecked climate change, and future generations will benefit from the climate stability this helps preserve. Others counter that this argument depends on assuming nuclear accidents are rare, but we have actually experienced several major nuclear disasters in the relatively short history of nuclear power. Beyond Chernobyl, there was the 3 Mile Island accident in Pennsylvania in 1979, the Fukushima disaster in Japan in 2011, and numerous smaller incidents. If we continue building nuclear plants and operating them for decades, are we essentially guaranteeing that more Chernobyl-scale disasters will eventually occur? And unlike climate change, which is a gradual process that humanity could potentially adapt to, nuclear accidents create immediate catastrophic contamination of specific areas. Moreover, the waste problem remains unsolved. We have been generating nuclear waste for over 70 years, yet we still have not successfully created a permanent disposal site for high-level waste anywhere in the world. Are we justified in continuing to generate waste that we demonstrably do not know how to safely dispose of? The debate over nuclear power's future has taken on new urgency as countries grapple with the need to rapidly reduce carbon emissions. Some nations, particularly France, which generates about 70% of its electricity from nuclear power, view nuclear as essential for decarbonization. Others, like Germany, have decided to phase out nuclear power entirely, choosing to rely on renewable energy sources like wind and solar along with natural gas as a transition fuel. After Fukushima in 2011, Japan shut down all of its nuclear reactors, though some have since restarted. China and India are building new nuclear plants as part of efforts to reduce reliance on coal. The global nuclear industry argues that new reactor designs are far safer than older models like Chernobyl's RBMK reactor, incorporating passive safety systems that will prevent accidents even if all active cooling systems fail. However, critics point out that every nuclear disaster was unexpected and involved failure modes that were not anticipated by designers, suggesting that new designs may also have unforeseen vulnerabilities. Perhaps the most important lesson from Chernobyl is not whether nuclear power should or should not be used, but rather the need for profound humility about the long-term consequences of our technological choices. The engineers and politicians who built Chernobyl in the 1970s did not anticipate the disaster that would occur a decade later, nor did they foresee the enormous and lasting consequences that we are still grappling with today, nearly 40 years after the accident. They could not have imagined that in 2025, people would still be working to contain the contamination, that vast areas will remain uninhabitable, that the cleanup would take decades or centuries and cost hundreds of billions of dollars, or that radioactive contamination would continue spreading through forests, water systems, and wildlife. This suggests that we should be very cautious about creating technologies that can produce consequences lasting far longer than our ability to predict or control them. Chernobyl stands as a monument to human ambition, human error, and the terrible persistence of our mistakes. The disaster reminds us that we are connected across generations, that our actions today shape the world our children, grandchildren, and descendants thousands of years hence will inherit. It challenges us to think more carefully about the long-term implications of our technologies and to ask ourselves whether we have the right to impose risks and burdens on countless future generations for the sake of present benefits. The most hidden risk of Chernobyl is not any single pathway of contamination or health effect, but rather the demonstration of how a single moment of catastrophe can cast a shadow that stretches across centuries. It is a revelation that some mistakes cannot be fixed, only managed, and that this management will require sustained effort, resources, and vigilance from generation after generation of people who had no role in creating the problem. As we face other long-term challenges like climate change, artificial intelligence, biotechnology, and the accumulation of various types of persistent pollution, Chernobyl offers a sobering case study in how present actions can burden the future in ways we cannot fully anticipate or control. The ultimate lesson is that we must approach powerful technologies with greater wisdom, foresight, and concern for those who will come after us, recognizing that we are not the only generation that matters, but merely custodians of a world we will pass on others. If you enjoyed the video, don't forget to leave a like and subscribe to the channel so you don't miss any videos. See you next time